In this lecture, we're going to be talking about geohazards. And if this is something that you really like, there's other natural disaster classes that you can take so you can learn about all of these things I'm going to cover in one lecture spread throughout a semester. We've talked quite a bit about geohazards when we talk about earthquakes and things like that. So these are just a few more examples of geohazards. And some of these hazards we can experience here in Southern California. So some of the things I'm going to go over, of course, there's more geohazards than I have listed here, but these are just some of the things that I think are interesting and maybe you find interesting as well. So during this class, we're going to learn the characteristics and consequences of different types of mass movement, the factors that determine slope stability, things that can trigger movement or a geohazard event, why some regions are more susceptible to hazards than others are, and how to identify these geohazards, and in some cases, how to prevent them or how to prevent loss of life or loss of property. So in this lecture, I'm going to be giving an introduction to some of these different hazards, and then I will sometimes I'll embed YouTube videos in there, or I'll give you examples of YouTube videos. One thing to note is that when we talk about geohazards, and things that are captured in video, sometimes they're quite devastating and can be sensitive to watch. So I would just say that if you do get into a rabbit hole of looking at some of these videos and some of the firsthand accounts of someone experiencing these geohazards, I just want to caution you just in case you are sensitive to that sort of thing, because generally when we talk about these really devastating events, there's typically loss of property and typically loss of life. So let's first talk about mass movement. Mass movement, or also called mass wasting, is the downslope transport of rock or soil or debris, or sometimes snow or ice. And this feature can cause damage to environments and societies. So let's think back to the rock cycle. If you remember, go backwards and remembering what the rock cycle is, how does mass movement play a part in the rock cycle? Well, mass movement is a component of, it could be a deposition, a transport and deposition of sediment. So that would be part of the rock cycle, and how you might have igneous rocks turning into sedimentary rocks through transport. So what's an example of mass movement? Well, we got landslides. So a landslide, here are some features of it. First is the type of material involved. Usually it's a loose soil or some sort of debris. Second is the velocity of that movement. Is it moving slowly? Is it moving really quickly? There's different characters of the mass. Is it coherent? Is it one large coherent mass? Or is it a slurry? Is it really chaotic? Is it really churned up? And then the environment in which the landslide takes place. We have things that happen on land or subaerial, or things that can happen underwater, like a submarine. So there's two different, when we talk about the velocity of a landslide, we can usually define it into slow or fast. And slow refers to a creep movement. And this is where you have a gradual downslope of the regolith on a slope. So here, if we have sediment or loose soil on top of underlying bedrock or rocks underneath it, this is the zone of creep where you have that loose sediment, that soil that's just sitting on top. And over time, what happens through freeze thaw, or if there's a change in cooling or change in rainfall into the system, you would have a slow creeping of that topsoil. You might have experienced this with if you have a lot of swelling clays or something in your soil, and it breaks up the sidewalk. I'm sure you've experienced that, where you notice over time certain neighborhoods have more cracked sidewalks, and they're unevenly sloped, and that has to do with the swelling clays that absorb material and expand, and then as it dries out, they don't swell. So that continuous increase and decrease in volume causes creeping. And if you're on a slope, then that causes the creep to fall down that slope. And another example of this is a slump, where you have a huge coherent mass that moves all together. And a slump is typically faster than just a creep. So when we talk about a landslide, this is like a large landslide event. This is a mass that moves all at once in one coherent mass here. And that mass is often referred to as a slump block, like where the whole block moves together. Sometimes it's planar, but most of the time it's curved. And along this surface here is like the failure surface of that slump. So when we talk about where landslides occurs, they have to have some slope associated with them. And slope stability has to do with gravity and the resistance to gravity. So if we have a general slope, we have gravity that pulls downwards, and if that slope increases, if it gets steeper, your resistance force exceeds the gravitational force and causes the mass to move. Like, imagine trying to walk up a really steep hill. That's much harder to do than a very gradual sloping hill. It's the same sort of thing applies. So if there's an instability in your slope, that's when you have movement. So here's an example of a landslide in our backyard. I have a video where I go and check this out myself at La Conchita. So you may have not noticed this before, but if you drive up Highway 101 at the town of La Conchita, you can see that there's a large landslide that has happened there. And this landslide has occurred in the past as well. In 1995, there was a large slump, and in 2005, it happened again. And they actually built these barriers to protect some of these homes, but then the landslide just moved across the barrier and then buried some of these other homes here. So in 1995, this whole area came down, and they did a study and said, yeah, this area is prone to landslides. And then it happened again. And this time in 2005, there was actually a lot of loss of life. There's about 10 people that died in this event. So what would you say to the people that live here in La Conchita? If you're thinking what I'm thinking, it's maybe this isn't the best place to rebuild your home if it's prone to landslides. So next time you go up to Santa Barbara, take a look on the east side of the highway as you're driving past La Conchita and see if you can spot this landslide. Okay, so another mass movement example is a mud flow or debris flow. So a mud flow is like a landslide, but it usually involves a slurry of mud. And debris flow is like a mud flow, but it has larger pebble or boulder fragments. So this is just a change in nomenclature here. So debris flows typically have much larger boulders versus a mud flow, which has maybe more consistent muddy slurry. And so some mud flows start as slumps, but then they increase the water content and increase velocity. So an example of mud flows and debris flows recently was the Montecito mud flow that was a result of high influx of water. So during the Thomas Fire, there was not as much. The whole hillside was burned, and therefore water was not able to absorb into the ground. And so when there was a huge amount of water, it just ran right off the surface and carried with it these large a slurry of mud, and then actually further up it created these it pulled all of these large boulders and pebbles with it as well. So here's a video link to some landslides. I'm going to just provide the link to you. I recommend that you go check out some of these YouTube videos. I don't want to embed it again because some of these instances can be a bit sensitive to watch. Some of them are really interesting and you just see the river of the mud going by you. But sometimes, like when we talk about the Montecito mudslide, there's people who have lost lives, and of course it being so close to home that I'm sure that some of you were impacted during that time. Okay, so let's talk about another hazard, an avalanche. This is a mass movement, but having to do with snow or ice. And an avalanche is triggered when a large drift or snow builds up on the lee side of a windy mountain summit, and then it gives way and then knocks down all of the snow with it. And it can create a failure, much like a landslide, but instead it's with snow or ice. And wet avalanches can move like a slurry of solid and liquid water. So here's an example of the scar that's left over from an avalanche. You can see that it has taken all of the trees with it, and all you see is the rock beneath, the rock face. So this is an area where an avalanche occurred, and because of all of that movement and all of that snow just ripped up the trees as it went down the mountain. So here are some videos about avalanches. One of the videos shows how important it is to purposefully trigger an avalanche. And so as you watch that video, maybe think about why you'd want to trigger an avalanche. And really it's because if you can control where the snow falls, or if it looks like the slope is about to collapse, you don't want people skiing on it, or you don't want the village below to be impacted from an avalanche and a lot of snow collapsing down. Okay, another type of hazard is a sinkhole. So a sinkhole is an area of ground that has no natural external surface drainage. And so when it rains, the water stays inside and drains into the subsurface. So a sinkholes are common where the rock below the land surface is usually a limestone or carbonate or salt bed, and that can be dissolved by the groundwater that's circulating around it. We don't see this a lot with in areas where we have a lot of silicates and things like that. It's mostly where water dissolves away carbonate rock. And so as the rock dissolves away, there's spaces and caverns that develop beneath the surface. And there's 3 different types of sinkholes. I'm not going to go into the details of them, but we have dissolution, cover subsidence, and cover collapse sinkholes. And there's lots of cool videos of sinkholes that just like suddenly open up and can swallow whole cars. That's really interesting to see. Again, we see those most of the time associated with evaporate rocks and karst and carbonate rocks and things like that. So here's an image of where we typically see sinkholes around the United States. No surprise to me is that we see them mostly in the south here, like near Texas, where we have a lot of carbonate rocks. We have a lot of evaporate rocks that are associated with salt and things like that. We don't have too many of them that occur naturally due to the subsurface in California, but sometimes they do. And maybe that's because they are man-made sinkholes. And sometimes we do that unintentionally, like when we have to dig out for an infrastructure, or maybe if we're placing pipe, or if like we're building roads or something, and you put new material there, and without really realizing that perhaps you built a road on top of an area where there's water flowing naturally underneath it, and it's creating a cavern underneath something that was man-made. So of course, sinkholes can also be man-made, and sometimes we see this in our driving around, especially in wintertime where there's a lot of rain and we drive over it. We drive and drive and drive and drive, and it creates these divots and it creates these little mini sinkholes because of how asphalt can behave with cars driving on top of it and the incorporation of water as well. So here are some cool videos about sinkholes. Again, I'm going to just link all of these for you instead of embedding it into this lecture. Okay, tsunamis. Now, I think tsunamis are really interesting, and there have been a lot of tsunamis that have devastating impacts. So let's talk about how tsunamis occur. So a tsunami is a wave of water that's produced by displacement of the seafloor. And we can see this, we talked about this in the context of an earthquake, like the big tsunami that impacted Japan in 2011, I believe. And so that tsunami was catastrophic for the populations that live near the coast. We can also have a tsunami as a result of a volcanic explosion or a submarine landslide. And these types of things would create a displacement of the sea floor, or just a huge influx of water that would create this wave that would then hit the coastline. So tsunami comes from the word harbor wave in Japanese. And as a wave approaches the shore, we have friction between the base of the wave and the seafloor at the bottom, so that the wave catches up and builds as it approaches the shore. And here's an example of that. So if we have a fault, for example, like in the earthquake near Japan, this created a huge increase in sea level, like a sudden increase, and that's what caused a huge wave to crash towards the shore. And for those of you that are into surfing, you probably are aware of how waves build and how you can count waves as they come approaching the shoreline. So so this kind of reflects the bathymetry, the below surface sea level, the topography of the ocean, so to speak, and how the bathymetry can really change the way that waves build as it approaches the shore. Again, here are some videos on some tsunamis, and I recommend you check them out. If you look at ones specifically for Indonesia, they can be quite devastating. Those are some firsthand accounts of watching the wave coming in. Again, it's very interesting, but I caution you against them if you're sensitive to that. One of the things that that we think about as a hazard, but how realistic of a hazard is it, is a meteor shower. The Earth, so Earth impact hazard, the danger of collision with other meteors or asteroids can collide with the Earth, and we actually get to experience those more often than you think. A lot of them do burn up in the atmosphere, but some of them do hit the Earth somewhat infrequently. And these can pose danger to people. Like if you get hit by one, that would not be fun. Or of course, damage to property. So how often do meteors impact the Earth? So this map shows, let me close this here. So this map shows some of the meteor impacts based on age. So over 1 million years old are red here, and more recent ones are in like a purpley bluish color here. And the size of the circle is how large of an impact it was. So we can see where we are in California, there's quite a large one that was between 400 and 1,000 million years ago. Okay. I got that backwards. Okay, edit this out. So here's a map of the meteor impacts that have happened in measurable time. So here in red is less than 1 million years ago. So these are the most recent impacts. versus the purplish and bluish were over a few 100 million years to 1 billion years ago. And the size of the circle corresponds to the size of the impact. So anything less than a kilometer is an X, and of course the size of, here's the size of a 10-kilometer impact, but some of these are much more devastating. So in California, it looks like the last impact to us was over between 400 and 1 billion years ago. The one that people seem to be most interested in is the one that hit Mexico that wiped out the dinosaurs. This is the Chicxulub crater. I always mispronounce this, but this is the crater that's beneath the Yucatan Peninsula. It's named after the town that where you can see the impact here, and the date of the impact coincides with the Cretaceous and Tertiary boundary, and I talk a little about this in the fossils lecture. So less than 66 million years ago, there's an accepted theory that the impact of the meteor created a climate disruption, which caused a majority of species to go extinct. And that's because the crater created this, it pushed up all of this dust that circulated around the planet, and it heated the planet and caused a disruption in the sunlight, and therefore caused a lot of food chain disruption and things like that. And so this is the extinction of a lot of species during the boundary between the Cretaceous and Tertiary boundary. The crater is estimated to be 93 miles in diameter and 12 miles in depth. That is huge. And it sank into the continental crust between 6 and 18 miles. So depending on where you measure, that is very deep into the earth. Here's an image, I think this is a LiDAR image that we see of the crater impact. And here's some evidence of that global impact. We can see the KT boundary here, that's this ashy layer. And this is an example near Red Rocks Amphitheater in Colorado. And we see it very clearly here, this band. And scientists have been able to look at this band of ash and glass shards around the globe. So we know that this impact was a global phenomenon. And we don't see fossils above or past this boundary. So this is an indicator that something huge happened, and we do not see fossil evidence of a lot of species on the other side of geologic time of this boundary. There's a really interesting podcast about this that I'm going to link in Canvas as well. So if you're interested in learning more, you can check that out. Here's an example of a meteor crater in Arizona. The meteor crater is about 1 mile in diameter, and it was created from an impact about 50,000 years ago by an asteroid diameter of 160 feet. So a 160-foot asteroid created a 1-mile crater. So imagine how large that asteroid was that hit Mexico to disrupt the entire planet. So the energy released was between 15 and 40 megatons to create this crater. So how many asteroids disintegrate in the Earth's atmosphere? How often are we hit with asteroids that don't make it to the surface? So a lot of them are burned up in the Earth's atmosphere. And so if we look at data between 1994 and 2013, this might surprise you to see that we have so many of these asteroids that are disintegrated in our atmosphere that don't even make it past and don't make it to our planet itself. So it's fairly frequent that we have asteroids that could impact the Earth, but they don't, they get burned up. And so what if an asteroid hit Los Angeles? What would happen? Don't get freaked out by this video if you choose to watch it. It was mostly made to be a joke because we can go through the what if all these things happen. What if there's a tsunami? What if there's an earthquake? What if there's an asteroid impact? And these are all things that are great to understand, but we also have to understand that most of these things are in a geologic time frame. So if we think about what's the likelihood of a tsunami happening, well, we have to look at geologic history to understand how frequently they happen, and is it really likely to happen in our time, in the way that we measure time in years and decades versus geologic time of hundreds, thousands, and millions of years. So don't get too worked up about whether or not geohazards might happen to you. It might happen to us in Southern California, but it's just an interesting way to look at some of the processes that are happening around us. Okay, so some of the things that we talked about are mass movement and how they're related to slope and slope stability. There's a lot of things that can trigger mass movement and what we call a geohazard event. We talked briefly about sinkholes and avalanches and meteor impacts. So there's a lot of different geohazards that can impact our everyday lives, but with a caveat that sometimes these are framed in geologic time and not in real time. If you want to learn more, there's tons of YouTube videos and resources that I'm going to post for you to learn more about this. This is just a brief overview of some of the hazards, and I recommend that you check out the YouTube videos associated with this lecture.